and join me here for the discussion on how we leverage AI for hazard analysis for autonomous vehicles. My name is Edward Schwalb. I'm a data scientist at the company called MSC Software. My background is mostly artificial intelligence, automated reasoning, and machine learning. The company is a simulation company. You can see here we have quite numerous products, different types of simulations, mechanical engineers and vehicle dynamics, and lots of different types of simulations. The one that I'm talking about here relates to this product. Let me show you the video of what our product is. I hope you guys can hear.
Yeah, able to hear you. Edward?
Could you guys hear it? I hope you can see it. If not, I'll
Able
move on.
to see your screen?
Okay. Okay, so then I guess I wasn't sure. Could you hear it though? Was the audio playing?
Audio not
No.
perfectly.
No. Okay, that's fine. Okay, so I'll move on to the presentation. So the
Sure.
company MSC Software was acquired by a larger company called Hexagon, and so as part of that we have numerous other products that were added. And so here I'm going to focus specifically on hazard analysis for autonomous vehicles and how do we address this problem. So let's start about talking about the scope of the challenge for those not in the industry. You may or may not know that humans, if you add up the list of all the miles that people drive and divided by the number of fatalities on the road, there's about 90 million miles between fatalities. So we drive 90 million miles for every fatality we observe in the United States. So even though we have 30,000 fatalities, we do have more than 3 billion miles traveled. And but if you do statistics on a vehicle by vehicle basis, because this is more important, the autonomous driver needs to be as reliable as the number of miles a vehicle travels between fatal crashes, not a driver. And that would be more between 200 and 400 million miles. That's a big number. And so we need to build AI systems that are not 99% accurate, not 99.99% accurate, but 99.99999, many zeros accurate. And so the implications of that is that autonomous vehicles would have to be driven billions of miles to demonstrate their promised rate of fatalities and injuries. And that existing fleets will take dozens of years to drive these miles. And so it means that physical driving alone cannot provide sufficient evidence for demonstrating autonomous vehicle safety. We know that. Yes, we do have people that are claiming to be on the road, but they have not demonstrated, nor do they claim that they have demonstrated achieving the safety level that humans have. They do have voluntary safety statements, but they would never argue that they are better than humans. They don't have the data to support it. At least I haven't seen it. But the upshot of this whole thing is you need to have virtual testing, because the only place you can run billions of miles is in simulation. And so what we do, our products and our efforts are to make it practical, possible, and take the results from simulation and make sure it carries to the real world. To give you more of a perspective on the industry, please note that if you do look at the list of all the crashes as reported by the National Highway Transportation Safety Agency Administration, less than 1% of the crashes are because of vehicle failure. So there's a whole industry of vehicle safety, and there's a lot of vehicle safety standards that have to do with making sure that the vehicle doesn't break. So how the control system works and how the steering and braking works. And one of those standards, for example, is the rear view mirror. That is really useful for humans, but I don't think that self-driving cars or autonomous drivers need rear view mirrors. But the bottom line is that the safety industry as a whole is only addressing the failure portion, which is less than 1% of the problem. And the remainder is basically behaviors, multi-agent behavior of the different traffic participants. And so what it means is that when we increase automation, so if you're familiar with SAE levels of automation, level 2 means no automation or limited automation at all. But level 3 and above means that the vehicle starts responding automatically, steering automatically, braking automatically. For example, advanced cruise control is what we call 2.5. There's some level of automation, but it's very limited. And so that means because we are looking at multi-agent hazards, that scope of residual risk increases more than 100-fold. And again, yes, I know people like Elon Musk are claiming they will have autonomous vehicles, but be careful what you sign and read the small print, because they relieve themselves of liability. And so in order to make this thing work, please realize that on the road and in simulation, it is very difficult to control individual outcomes. It's impossible to control individual outcomes, mostly because the systems, the underlying system are non-deterministic. For example, robot operating system threading are causing non-determinism issues. But in order to achieve the results, we have to control the aggregate statistics. So this is an example where when we test something, we cannot guarantee outcomes for a specific scenario, but we have to be able to guarantee the overall statistics. The question is, what is that statistics? So one of the first things to remember is that statistics is complicated and the problem is complicated. So I'm going to show you 3 examples. I'm going to talk a little bit about some solutions and some experiments that we conducted that you can also conduct to convince yourself that this is the case. This is just for informative. We're not selling anything to anybody here. Just some interesting things. So one of the examples I usually give is in November 2018, an autonomous shuttle was deployed in Las Vegas, and in one of its trips it encountered a semi-trailer truck. The truck was backing up and slowly but surely, eventually it grazed the shuttle. It was getting closer and closer until it grazed, meaning the truck scratched the bumper in the front of the shuttle. So city officials said that the shuttle did what it was supposed to do, and that sensors registered the truck and the shuttle stopped. And really, is this the requirement? Really what we expect from autonomous shuttle with passengers in it, that if a truck is backing up into it, it will simply wait for it to get squished? What would happen if the truck would be a few feet further? Passengers said that we had about 20 feet of empty street behind us, and most human drivers would have thrown the car into reverse and used some of that space to get away from the truck, or at least lean on the horn and made our presence harder to miss. Now, remember, there was no requirement for software engineers to guess what they could ever do when a truck comes and crashes them. And it's very difficult to come up with all possible answers to the situation, but it is required. It seriously is required, and according to NHTSA, more than 3% of the accidents have this pattern. So it's not an edge case, it's a very common case. We're talking about easily 1,000 accidents a year, easily. Here's another example. so I guess before I switch over, the point here is we have a solution, and you're encouraged to reach out to see how we actually automatically find the right action and to achieve accident avoidance. And how do we train for it? I don't have time for this detail here, but here's another example, which is, I bring it here because if you are a US based person, or if not familiar with the driving laws in United Kingdom, I would like to know that in United Kingdom, the theoretical driving test requires that you identify hazards on the road against the video with a clicker. So the video is playing and you're supposed to click when you find those hazards. As examples, the training videos will give you is they would mark those potential hazards, things that could go wrong, as yellow circles. So for example, the pedestrians on the left side could jump into the path of the car from the sidewalk onto the street. There's a small easement where cyclists can come on the side street over there. You can see the vehicle in front of us may stop. And then there's parked cars on the right. So that means pedestrians can emerge from between those cars or walk towards opening the doors, and you can have drivers that open the doors of those cars. So all these are things that potentially would happen. And so our AI needs to detect those and then estimate how far they are. So for example, when you look at the vehicle in front of you that has stopped, and this is like a few frames, a few seconds later, then that vehicle in front is distance away from us. We have to slow down to avoid the crash. If we don't slow down, we will rear-end that vehicle. And so we will have to slow down and accelerate, and all this behavior, which is complicated. I'm showing this to you so you understand there's an interesting requirement to not only detect those hazards, but also handle gracefully the actions that mitigate those accidents. So the upshot, what I want to talk to you about here is that we need to have those hazard detectors trained for very rare events. Now, to give you a perspective, when you drive, you rarely encounters on the freeway, you rarely encounter pedestrian coming between the parked cars. And in many cities in the United States, we don't even have parallel cars that you have to worry. You just go to parking structures. And there's many other rare events like pedestrian jumping in front of the car, like happened to Uber. These are rare events, but yet the system needs to be trained for those. But why is it challenging to train for rare event? So let me give you an example why rare events are bad. If somebody tells you that I have a hazard algorithm which is 99% accurate, is it good? Well, the answer is not really. It's actually very bad, because if we have something that happens 1 in 1,000 or 10,000, 100,000 driving hours, then if you just guess it doesn't happen, you will be 99.999% accurate. So if something is rare and only happens 0.1% of the time, guessing it will never happen will give you 99.9% accuracy. So this is a picture from something called SMOTE, S-M-O-T-E, which is a synthetic minority class oversampling technique, where in machine learning you would say, well, if my minority class is very small and rare, then I'm going to create more examples from the minority class. So those red dots represent the minority class, and the green dot represent newly generated data that will represent those hazards that we would like to train. But that will not work it will work for verification, and I'll explain that in a minute, but it does not work for training, because if I train for the wrong distribution, the performance I observe in training and the model that I'm getting is only good for the skewed distribution, is not going to be good for the true distribution. And because we are talking about increasing the frequency, not 10%, but rather 10x, 100x, a million x, that makes a big difference. The skewing now makes the model not as good. So that's part of the challenge. You have to train for very rare events. So what did we do? An experiment we did, and you can do it yourself if you want. Imagine that you have MNIST digits to detect as opposed to hazards on the road, just to give you very simple. And so if you want to do a test, you can take the MNIST data set and then generate a data set in which the minority class, let's say we are classifying only zeros, we want to detect those zeros, the minority class would be 0.5% of the majority class, for example. So 99.5%, we have any other digit than zero, and then only 0.5% we put zero there. And so what we need to do is we tested a mechanism where instead of skewing the distribution, we are generating more digits. We are amplifying the scenarios. We are like we do in PCR. In genetics, one of the major breakthroughs is ability to replicate the DNA to have sufficient quantity that you can do experimentation with. And here the situation is very similar. We need to take those rare situations, rare events, and we need to amplify them and generate more of them so that we can do some meaningful training. And so here's what I'm showing you, the result of what happens if you do it correctly or incorrectly. So the blue line represents the four metrics. We are presenting here the metric of true positives and true negative, false positive, and false negatives. And where accuracy is the sum of true positives and true negatives. And so what we're showing, the blue bars represent if you would have done MNIST training the traditional way, just like we are told in the books, and we get 99% accurate. And so what we can see is that the learning that we get with the blue bar is very reasonable. We get pretty good true positive and true negatives, because we are giving it the entire data set fully balanced, as you know, as the original training was designed to be. But now we removed all those zeros, and we only exposed the training algorithm to 0.5% of zero digits. Everything else is non-zero. And now we're asking it, how well is it going to learn? So the orange one represents how well it learned. So you can see that it still learned pretty well. It's pretty impressive, actually. You still get roughly a 50% positive rate, which is, of course, better than 0.5%. So it's learning something. But it's only 50% accuracy, true positive rate. The true negative rate obviously is very high, because the minority class is less than 0.5%. So obviously we are still keeping the, by guessing mostly that the hazard is not there, it will still show very high results. But what's very interesting is you get very, very large number of false negative. What is a false negative? False negative means there was something on the road that you didn't detect and you could crash for it. It's very interesting. And so if you do the amplification, you get the green bar, which represents, okay, now this is what happens if you use this PCR technique that basically says, yeah, I can amplify and remove my false negatives dramatically so I can detect more of the hazards. So the general idea would be that there needs to be some statistical approach. So if you look at it from Bayesian perspective, the probability of a crash is the summation of the probability of a crash for a given scenario multiplied by the prior of that scenario. And so if you extend this to using hazards, you can further decompose it. You can see that there's the probability of the crash for a given hazard, which is called controllability. How well is the algorithm avoids accident? So that controllability is the accident avoidance component. And then the probability of a hazard existing for the scenario has to do with exposure. How likely is the pedestrian to be on the freeway? Or how likely is the event of Uber to happen to us? And what we do in simulation, we can automatically generate distributions that will increase those probabilities of hazards. So it will learn what the emerging hazard is and will generate, and there's so many different types of hazards that are nothing to do with crashing. So it wasn't one of the examples. I want to show you a quick video. So what you see here, this is Tesla, as you can imagine. And what happened is that we're engaging advanced cruise control. The lead vehicle is moving out of the way and we have a crash. Now, mind you, all the vehicles in the industry have this problem, not just Tesla. We can't even do this, not to mention autonomous. And so this is showing you that a very simple challenge. You have to find out exactly what combination of parameters makes the least score lower. Here, I don't have a video showing because for whatever a video is not showing, but here we show the exact simulation of that scenario. And I would like to tell you that more than 1% of the crashes are represented by this example. And here are different reasons why the vehicle might be stopped, maybe waiting for pedestrians to cross, or maybe we have a bicycle we're trying to go over, or maybe a pothole or tree on the road and such. And so we need to train the machine learning on those rare events to know how to do. So how do we model? We have to leverage distribution. In one of the experiments that we did, we said, okay, let's train our neural network to detect the distance to the vehicle in front of us and see how it performs. So we trained it on sunny days images and scenarios, and then we tested it on dusk and snow scenarios. And we found out that the neural network overestimates the distance, says it's higher than it really is when I test it on distributions other than what it was trained on in the dusk. So I trained on sunny days and I tested on dusk and snow, and we can see the shift. Now this shift is again unsafe because we would break later than we otherwise would if we haven't done that test. So the point here is that the accuracy by itself doesn't matter as much. You would argue the bias here is what matters, but the distribution matters more. So instead of just showing a single number that says this is my accuracy or this is my false positive negative, no, you need to have a distribution perspective because you want to know how far the distribution is and what would be a safety factor that you need to add in order to make it work. And so in one of our demonstrations, we show how we run multiple simulations in the cloud. And what you see on the top is the distribution of hazards before we run our sampling algorithm. And then in the bottom, how we generate only scenarios that have the hazard showing. So you can see the huge spike in likelihood of the scenario occurring on the target challenge hazard use case. And so the bottom line is that we need this PCR approach. We need a sampling approach for those scenarios to make it work. And you definitely cannot do that thing in the physical world. That's pretty much it. Basically, the idea would be that we would need to do machine learning to perform probabilistic analysis. So we train our algorithms of very rare events, and we cannot use mode because we are talking about minority classes that are way less than 0.1% of the majority class. And we need to do that over billions of the equivalent of billions, but we don't need to run those simulations because we have those PCR techniques. But the virtual development and testing using those techniques needs to be a first class. So if you just put the vehicle on the road and then you measure what happened, you have no chance. There's just not enough physical combinations to cover all the multi-agent scenarios you need. And you need to work with AI that trains and validates on extremely rare scenarios. So if it looks okay, even 99%, it's terrible. If it is 99.99999% correct, that's good. And so I guess the message would be that we need to focus on probabilistic simulation of scenarios. We can't just look at individual cases at a time. So that's pretty much it.